The topic chosen for our presentation is Poisson Distribution. Group members Angela, Nithin, and Saristha.
What is Poisson distribution? In probability theory or statistics, the Poisson distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed time of space or time if these events occur with a non-constant mean and independently of the time since the last event happens. It is named after the great French mathematician Simon Denis Poisson.
The Poisson probability mass function can be written as shown on the screen. Here, lambda stands for the mean, and x can take values from 0 till infinity. The three conditions followed when a variable follows Poisson distribution are as follows. Number 1, data are counts of events. Number 2, all events are independent. And number 3, the average rate of occurrence does not change during the period of interest.
Let's see some applications and examples. Example number 1. Restaurants use the Poisson distribution to model the number of expected customers that will arrive at the restaurant per day. For example, suppose our college canteen Chopsticks receives an average of 500 students per day. We can use Poisson distribution to find the probability that it receives more than a certain number of students. That follows like P of x greater than 515 students, P of x greater than 525 students, P of x greater than 530 students, and so on. This gives the canteen managers an idea of likelihood that they will receive more than a certain number of customers in a given day.
Example number 2. Call centers use the Poisson distribution to model the number of expected calls in a given hour so that they know how many call representatives to keep on staff. For example, a given call center receives 10 calls per hour, and then we can use the Poisson distribution to figure out the probability that the call center will receive 0, 1, 2, 3, or any number of calls in that given hour. And to do this, we find P of x equal to 0 call, or P of x equal to 1 call, or P of x equal to 2 calls, and so on. This gives the call center managers an idea of how many calls they are likely to receive per hour, and it enables them to manage the employee schedules based on the expected number of calls.
Significance of Poisson distribution. Suppose we have a large number of independent events, say n events, each happens with a very small probability epsilon, then the total number of events happening is approximately a Poisson distribution with parameter n epsilon. More rigorously, if we denote the number of events which happen among the n events by m and assume that n goes to infinity and epsilon goes to 0 in a particular way such that n epsilon is equal to lambda for a positive constant lambda, then the distribution of m will converge in distribution to a Poisson distribution with parameter lambda.
Suppose we have events happening one after another. The amount of time between the occurrence of these events are independent and identically distributed exponential random variables with parameter lambda. Since exponential random variables are memoryless, intuitively, this means that at any given time, we still need to wait for an exponential amount of time until the next event happens, regardless of how long we have waited. In this case, if we count the number of occurrence of events in a fixed time period with length t, then we get a Poisson distribution with the parameter lambda t.
That's all about our small presentation based on Poisson distribution.
Hope you liked our video.
Thank you.